Okay, talking about angle observations, okay, when you do traversing, so when you use this equipment, the total station, when we measure angles have to be measured twice, okay, and we term that as face left and face right, okay. So if we have equipment like that, okay, as shown the total station, when we measure any angle, we have to measure it twice, once in face left and one in face right. So what does that mean? What's this face left and face right now? Okay, by definition, face left reading simply means that any angle that we observe when the total station is on face left, and similarly, face right simply means that when the station is on face right. So how do we tell whether we are on face left or we are on face right? So there are several ways of doing that, okay, but I think the most easiest way using a digital equipment like this would be simply by looking at the horizontal angle. The vertical angle. If the vertical angle reads 90 degrees when the telescope is horizontal, then you know it's face left. But if the telescope is horizontal and the vertical angle reads 270 degrees, then you know you are in face right. So that's the, I think, most easiest way to tell, even though some equipment has display indicator on the display to show that whether it's left or right. But in either case, okay, if you're not sure whether that's a display or otherwise, just get the telescope roughly horizontal and read the vertical angle. If it's 90 or close to 90, then you're on face left. If it's close to 70, then you are in face right. Okay. Now, just this slide is just to show the horizontal and vertical circle, okay, the reading that you obtain. How do we get those readings? Okay, vertical circle, basically start the telescope. Okay, there's a glass plate here, akin to a protractor, a whole circle protractor, 0 to 360. So whenever you tilt the telescope, the number changes, and that gives the display, gives the values on the display. And the zero value for that protractor is upwards, okay, towards the sky. We call it the zenith. So whatever above your head going up, we call it zenith. So 0 is there, okay. Whereas for your horizontal circle, which is a glass plate down here, okay, it's also like a protractor, a glass protractor, runs from 0 to 360, and is graduated clockwise, okay. And unlike the vertical circle, there's no specific zero direction for it. It depends on what we have set it on, okay. You are quite free to choose where your zero, which direction your zero is. I think you will see that later when we talk about bearing observation. But anyway, for now, the vertical angle, horizontal angle, basically given by a pair of glass protector, okay, and the 0 for the vertical is the zenith, whereas the 0 for the horizontal circle depends on the user, depending on what we have chosen. Okay, let's look now how do we go about changing from face left to face right. We talk about face left, we talk about face right, we talk about observing angles in two faces. So how do we go about doing it? What does that mean? Okay, I've got a figure, a picture of theodolite, okay, similar to a total station, but in this case a theodolite, okay, a top cone theodolite. Okay, the axis that runs through the telescope, 90 degrees, okay, to the telescope, is called the trunnion axis. This is the axis where the telescope can be rotated about. Okay, you rotate the telescope about the trunnion axis. Okay, and let's say we are observing now from the rear of the telescope at point P, okay, to point P. Let's say now we are in phase left. We notice that the vertical angle was close to 90 when the telescope was horizontal, so we know that it is in phase left. Now, what we're going to do next, if you're going to change phase, you've got to flip the telescope about its trunnion axis. Okay, either you go down or up, doesn't matter, until you are 100, looking the other way, facing the other way, or the telescope is flipped 180 degrees. Okay, so now the eyepiece is away from you. Right, so like shown in figure 3. Then you have to rotate the telescope 180 degrees so that the eyepiece will be close to you, next to your eye, so that you could measure point P again now, but in phase right. Okay, so phase left, measuring P, phase right, measuring the same point P. So that's what I mean by changing from phase left to phase right. Okay, supposedly, okay, assuming that we have, or we read 20 degrees here, when we're in phase left. So when we have changed phase to right, we should read 200 degrees because we have rotated 180. So 180 plus 120, so that should give us 200 degrees. Okay, right? So in other words, okay, when you do your observations, you got two sets of readings. You got two readings, one on phase left and one on phase right. So the simplest check that you could do, phase left and phase right, the difference should be 180, close to 180. Okay, and we cannot say 180 exactly because we might have errors in our measurement. But this is a indicator, or this is a thing that you always have to do when you measure phase left and phase right, just to make sure that you are measuring or you are reading the right numbers. Okay, anything close to 180. Okay, so that is for your horizontal angle. So how about vertical angle? Okay, what I have there on the screen is total station phase left, which means horizontal 90, okay, zenith up and towards the sky, and 270 the other way, 180 pointing down. So if I have a point Q, which is a bit higher than the instrument, and I read, or the total station gives me a reading of 82 degrees. So that means, okay, my angle is actually 8 degrees. Okay, my angle is actually 8 degrees elevation. Now, when I change phase to phase right, now that panel now is moved to this side now, so I'm on phase right. So my 90 now is on this side. So if I'm observing from there, so my horizontal now is 270. Okay, it's no longer 90. So for the same point, point Q, if I were to point the telescope to Q, if I were to read the vertical angle, I will get 278, which is 8 degrees there, plus 270. So that's 278. So how do we check? We take the sum. Unlike the horizontal where we took the differences, but in this case we take the sum, and it should be close to 360. Okay, close to 360, and the angle that we require is 8 degrees. Okay, so just remember that horizontal angle, face left, face right. To check, the difference should be close to 180. Vertical angle, face left, face right. To check, the sum should be close to 360 degrees. Okay, now, so that's angle observations, how to handle, how to understand how the total station works, okay, in a way. Okay, so why bother? Why do you have to do all this? Why do you have to measure it twice? Why both faces? Okay, by taking the mean, if you got one on left, one on right, if you take the mean, you could basically eliminate the collimation error. Okay, similar in leveling, to eliminate the error in the collimation line, we make certain that the length of the backside and four sides are roughly equal. So in traversing, when you use a total station to eliminate collimation error, possibility for any collimation error, we always observe on both faces. Okay, so that's why we need to do that. We cannot skip this. If you skip doing this, there'll be no checks. You cannot be certain of the values that you have observed. Okay, again, as far as the vertical circle readings is concerned, by taking the mean, you will take care of any zero error. Okay, we call it the vertical circle index error, the zero error, the zenith. Okay, so let me just, I think the next slide shows schematic of how we eliminate collimation error. And of course, the third point on the screen there says to check against gross error. Okay, which simply means if you read on face left, let's say 45 degrees. Okay, so when you change face, you should read close to 225, because 45 plus 180 is 225. If somehow or other you have written down, or you have read like 215 or 252 maybe, then you know there's something amiss, something is wrong. So that's again is a good way to tell whether you have gross error. Okay, as I said just now, okay, let's look and what do we mean by eliminating collimation error by observing face left and face right. Okay, what we have this on the screen now, okay, what we have is a telescope, the collimation line, the blue line, and this axis here is the trunnion axis, okay, as written there. And it's obviously, if there's nothing wrong, if the equipment is okay, perfect, so there'll be 90 degrees, exactly perpendicular. Okay. However, okay, sorry, if that is the case, if I point it to a target, that point there, okay, if there's no other error, let's say it's perfect, in perfect condition, the angle is 45 degrees, okay, meaning that the collimation line is exactly 90 degrees to the trunnion axis. Okay, so we cannot be certain of this condition all the time, even though your equipment your total station is pretty relatively new, but still we cannot be certain. Okay, So what happened, okay, if I have a telescope with a collimation error like that, okay, the blue line now is no longer perpendicular, but now at a certain angle, okay. So if this is the case, this is what we term as a telescope with collimation error. So what happened if we use this without doing any checks? So obviously the angle that we'll be observing will be not correct, okay. So the next slide I think just show that particular situation. Okay, that's the actual angle, 45 degrees, when the equipment was like perfect, okay, nothing wrong with the collimation line. Assuming that there's a collimation line, the blue line, okay, so if I turn the telescope, when I get to the target, the equipment will read 52 degrees. We have gone past, because the collimation line now is not perpendicular to the trailing axis anymore. It's not perpendicular there anymore, and it's shifted to your left. Okay. Now, how do we get rid of that problem? If you flip the telescope now and change face, the collimation line will be on your right. It was on the left previously. Now it's going to be on your right because you're observing from there. That's where we will be looking through. So if you measure the angle to that point, you'll be getting 38 degrees here. Okay? You'll be getting 38 degrees there. Okay? So in face left, you've got 52. In face right, you've got 38. So if you take the mean of those two numbers, okay, 58 plus 32 divided by 2 actually, okay, you get 45 degrees, which is the actual angle that we want. So in other words, by observing face left and face right, we are able to eliminate collimation error. Okay, so that's why it's imperative for you to stick to this procedure. All angles should be measured in both faces. Okay, there's no excuse, okay, when it comes to measuring angle. Okay, so that's some explanation on face left and face right and its importance in determining or eliminating the collimation error.
انضم معنا الآن واشترك بالقناة ليصلك كل جديد. YSAG، معا نحو مستقبل مشرق.